In the previous video, we discussed using Venn diagrams as graphical representations of sets. For example, consider the following three sets. A is the set containing the elements 1, 2, 3, 4. B is the set containing the elements 2 and 5. And the universal set contains the elements 1, 2, 3, 4, 5, and 6. We can represent these sets graphically using this Venn diagram. So let's place the elements in the appropriate sets. For example, in the intersection of A and B, we can find the element 2. It's contained in both sets A and B. The elements 1, 3, and 4 are contained in the set A. The element 5 is contained in the set B only, and the element 6 is contained in the universal set but is not contained in either A or B. In this section, we would like to use Venn diagrams to represent the cardinal number information of the sets. So in this example, the intersection contains one element, A only contains 3 elements, B only contains 1 element, and the universal set contains one element that is neither in A nor B. From this information, we can answer a variety of questions. For example, what's the number of elements in the set A? Here the answer is 4. We get 4 elements because we are adding up everything in A, which includes the 3 and the 1. Another question we can answer is, what's the number of elements in A complement? Here the answer is 2, because we're adding up all of the elements that are not in A complement. There's one element here and another element here for a total of 2 elements. We could ask for the number of elements in A union B. Here the answer is 5, because we're adding up the 3 elements here, plus the 1 element here, plus the 1 element here. If we know how to shade the Venn diagram, then basically we are adding up all the cardinal numbers in the shaded regions. If we asked for the number of elements in the universal set, a common mistake is to say that there's 1, but in fact there are 6. The universal set contains all of the elements, so we have 3 plus 1 plus 1 plus 1. Let's look at an example of using Venn diagrams to help us answer questions about cardinal number information. Suppose a survey of 500 people asked the following 2 questions. Question 1, do you go to the movies at least once a week? Question 2, do you go out for dinner at least once a week? And suppose that 450 people said yes to at least one of these questions. 200 people said yes to number 1, and 400 people said yes to number 2. The question is, how many people said yes to both? First, we should develop some sets to represent the collection of people who said yes to the various questions. For example, we could let the set M be the set of people who said yes to going to the movies at least once a week, and we could let the set D be the set of people who said yes to going out to dinner at least once a week. Now we can write down the cardinal number information given to us in the problem. For example, this survey had 500 people, so the number of people in our universal set is 500. So remember, use a set, and U contains a list of 500 people. Next, we're told that 450 people said yes to at least one of these questions, which means that's the number of people in the set M or D. It's 450. We're told that 200 people said yes to number 1, which means that they went to the movies, so the number of people in the set M is 200. And finally, the number of people who said yes to question 2, which is that they go out to dinner at least once a week, is 400. So the number of people in D is 400. Now that we have this information, we can draw a Venn diagram. Let's see if we can use this information to fill in the Venn diagram. So we know that the number in the set M is 200, but the 200 is the total in both this region and this region. We know that the total in D is 400, but the total in D is this region plus this region. We know the total in M union D is 450, but M union D is the sum of these three regions. And finally, we know the total in U, but that's the sum of all four regions in the box. So we need to figure out something to find one of the single regions in this diagram. So we'll derive a new formula while we try to figure this out. Let's take a look at the number in M union D. Now, we can find this number as follows. We can add up the number in M, which means we've added this number plus this number. We can add to that the number in D, which means we've added this number plus this number. Now notice that we've added the center number twice. So we don't want to double count that number when we add up the number for the union. So what we'll do is we'll subtract off the number in M and D, the intersection, because we double counted that number. Now let's write down the information we know. We know that the union is 450. We know that the total in the set M is 200. The total in the set D is 400. And if we subtract off the number in the intersection, these two sides should be equal. So if you solve for the number in M and D, you get 600 minus 450, which is 150. So now we know the number in M and D, the intersection, 150. Next, we know that the total in M is 200. So if the total in M is 200, and we've already written down 150 in part of M, then the other 50 people must be in the other part of M. Likewise, we know that there are a total of 400 people in D, and if we've already written down 150 in part of D, the other 250 must be in the other part. That way we get a total of 400 people. And using the same logic, we've written down a total of 450 people inside the union of M and D, and there's a total of 500 people in the universal set, so there must be 50 people left outside of those two sets. Notice that in the process of filling in this Venn diagram, we answered the question we wanted to answer. The question we wanted to answer originally was, what's the number of people in M and D? The number of people that go to the movies and go out to dinner at least once a week. The answer was 150. In the process of solving this problem, we derived a very important formula, the cardinal number of a union formula. If you want to know the cardinal number in A union B, this can be found by counting the number of elements in the set A plus the number of elements in the set B, subtracting off the number of elements in A and B because those elements were double counted. Let's look at an example with three sets. The store collected data from 1,125 customers. They found that 450 like red, 375 like blue, 300 like green, 200 like none of those colors, 175 like green only, 25 like all three colors, 50 do not like green but like red and blue, and finally 100 like both blue and green. We will answer questions like what percentage of the customers liked all three of the colors, or what percentage of the customers liked exactly two of the colors, or even what percentage of the customers do not like green. We begin by writing down the information from the problem in terms of set notation. So first of all, the number of people in our universal set is 1,125. We'll let R represent the number of people that like red, or the set of people who like red, so the number of people in the set R is 450. We can see that if we let B be the set of people who like blue, the number of people in the set B is 375. If we let G stand for the number of people, or the set of people who like green, then the number in G is 300. We know that the number who are in R complement and B complement and G complement So they don't like red, and they don't like blue, and they don't like green, so they like none of the colors. That's 200. We also know that 175 like green only. So that's the number in the set G, and they're not in B because they don't like blue, and they're not in R because they don't like red. That's 175. We know that 25 like all three colors, so that's the number in the intersection of all three sets. They're in G, and they're in B, and they're in the set R. It's 25. We know that 50 do not like green, but they like red and blue. So they are not in G, and they are in B, and they are in R. They like red and blue, but not green. That was 50. And finally, the number that like blue and green is 100. Notice that when we say the number who like blue and green is 100, we know nothing about the set R. Some of those people might like red and some might not. Let's consider some basic techniques for filling in a Venn diagram. Suppose we have a three-set Venn diagram. Then any information given to us which represents the intersection of three sets or their complements is one of the smaller regions in the Venn diagram and can be immediately filled in. For example, this first piece of information, the fact that the number who are not in R and not in B and not in G equals 200, can immediately be filled in on the Venn diagram. That's the number of people who don't like any of the colors. So they're in the universal set, but they're outside of the three sets. Next, we have this piece of information, which tells us that the number of people in G and not B and not R is 175. So they're in the set G, but they're outside of B and R. And that's 175 people. If we shaded that region of the Venn diagram, we would shade this region, which is why we filled the 175 into that region. Next is this piece of information that says the number of people in the intersection of all three sets is 25. So we have 25 people in this region. Next is this piece of information that tells us that the number of people outside of the set G, but in the intersection of B and R, is 50. So those 50 people belong right here. Now we've gone through all the information that represents the intersection of three sets. So next we should look at information that represents the intersection of two sets. The intersection of two sets would represent a slightly larger region in the Venn diagram. For example, this region, or this region, or this region. Those regions represent the intersection of two sets. So we'll look at this piece of information next, the number in B and G. B intersect G is given by this region. We know that the total in B and G is 100, so if we've used up 25 in the center, the other 75 must go here. Next, we could use the information that tells us that the number in the set B, so in the entire circle B, is 375. Now we've already used up 150 in the set B, as can be seen by these numbers. So if there's a total of 375 in the set B, and we've already used up 150, that leaves us with 225 people that are in that portion of the set B. We can use the same logic for the set G. We've already used up a total of 275. There should be 300 people in the set G, which leaves 25 people in this portion of G. And finally, using the same logic with the set R, we've already used up 100 people in the set R, which leaves 350 people to be in this portion of R. We should notice that the numbers add up the way they should. For example, we know the total in R should be 450 people. If you add up all the numbers in R, they add up to 450 people. We know that the total number of people in G should be 300. If you add up all the numbers in G, they add up to 300. And you can do that with all of the information given. For example, the number in B and G should be 100, and yes, they add up to 100. Now we can answer questions like, what percentage of the customers liked all three? So like red and blue and green. Now first of all, we have to remember how somebody finds a percentage. If we want to find the percentage of people who like all three, we would want to count up the number of people who like red and blue and green and divide it by the total number of people in our survey. In this example, the number of people in the intersection, red and blue and green, is 25. It can be found by looking at this region. The number of people in the survey was given to us in the problem. That was 1,125. If we weren't given that number in the beginning, then we would simply add up all of the numbers in the universal set, which is every number listed in the Venn diagram. If you work this number out on your calculator, you'll find that this is approximately equal to 0.022, which if we convert this to its decimal equivalent is about 2.2%. We could be asked for the number of people who liked at least 2. Now, you can represent sets using words. Number of people who like at least 2. And to find this, well, first of all, we have to ask ourselves which people like at least 2 in the diagram. These people like both red and blue, that's at least 2. Red and green, that's at least 2. Blue and green only, that's at least 2. And finally, all 3, that's at least 2. So we want to add up all of these numbers, which gives us a total of 175 out of the 1,125 people, which is approximately 15.56% of the people. Notice that I use the percent symbol once I've converted it to a percentage. Otherwise, if it's given as a decimal equivalent of the percentage, I don't write the percent symbol.